All right, so we'll continue our sessions, which are going to be the lead code questions. Yeah. Uh, Today we are going to cover the next questions. So we've covered till merge k list, correct? So we covered till merge k list, and let's continue learning the shortest path in binary matrix. And want to do this, this, this. ये cover किया हमने actually. Have to do this shortest path within this. Okay. 1, 2, 3, 4. Merge sorted array. Copy list with random pointer. There you go. Lowest common ancestors. All right. So the question is, let's send this question first. This one. Code. That's the question that we are solving. So the question says, you are given two nodes, P and Q. Okay? So there's P node and there's Q node. And you want to find who is the lowest common ancestor for P and Q. So your P is 5 and your Q is 1. So your 5 is here and your Q is 1. So who is the common ancestor? Nearest common ancestor is 3 here. So 5 and 1 are the nearest common ancestor, 3. If you check 0 and 5, okay, 0 and 5, nearest common ancestor is again 3 here. Okay, 0 ancestor is going to be 3, 5 ancestors again going to be 3. The nearest common ancestor is 3 for 0, 5. For 7 and 6, right? So if you have 7 and 6, the nearest common ancestor is 5 here. Okay, for 7 and 6, the nearest common ancestor is 5. The node that we have, it is having 3 pointers: left pointer, right pointer, and the parent pointer. Okay, so at any given point, if you have a node, you know what is the left, what is the right, and you also know what is the parent. If it is a root node, it is not going to have a parent. All right. If it's a leaf node, it will have parents. Okay. Another example, which is here, value of P is 5 and the value of Q is 4. Okay. So 5 and 4. In this case, the common ancestor is 5 itself, because 4 is child of 5. I mean, is a descendant of 5. Okay. So the common ancestor for 5 and 4 is 5 again. So that is the answer 5. All right, so that's the question that is given to you, and we have to find out lowest common ancestor. Like we said, lowest common ancestor is the first ancestor that is available. Okay, let's think about this now. We have 3, 5 on all of these numbers. How to find the ancestor of 1 and 5. Okay, 3 here. So anytime we see a tree question, there are various ways of parsing the tree. First of all, for example, you can parse the tree using BFS and DFS. When you do it by DFS, you can parse it in order, pre-order, or post-order. So these are the three various ways of parsing the tree. Uh, when you do the BFS, again, you can do the same, which is you go level by level here. There's no pre, post, or in order in BFS. Okay. All right. So common ancestor. So what we can do here is 3, 5, 2, and 4. This is the information that is given to us. I can start from here. I can search for P. As soon as I get a P, okay, All right. So I can do it. One thing we can do is we can go all the way to find the P. Okay. So we know that when we start from here, P is going to be found here. Okay. And we can store them in the list here like this. So for P, in order to reach P, I have gone to 3 and then I've gone to 5. That's how I reached P. Okay. In order to reach Q, I have gone to, so Q is 1 here, right? So I have gone to 3 first and then I've gone to 1. Okay. So this is the path that I follow to get to Q. All right. And we can see here the common is basically this 3 and 3. This is the first common ancestor. Let's take a few more examples. Let's take the example where the value of P is 6. Okay. The value of P is 6 and the value of Q is 7. Let's take that example. So value of P is 6 and the value of and the value of Q is, let's say, 7. In that case, you went to 3, you went to 5, and then you went to 6. So that's the path you followed. Here, you went to 3, you went to 5, and then you went to 2, and then you went to 7. That's the path you followed. Okay. As you can see here, if we start from left side, okay, if you start parsing this list from the left side, the first item which is common in both of them is going to be your least common ancestor. So I start from here. I get this node, this node. Okay. Obviously, there's no matching to be done here. So I just move on to the next node here, 5. Okay. So as soon as I see that this 5 is matching, that means this is my answer. That's one way of solving it. Okay. So let me start the timer here. So for that, we need to go all the way to that node and make sure we are keeping track of this. And since we are getting to the node, putting it to the list, moving on to the next node, putting that to the list, moving on to the next node and putting that to the list. So this is, and then we have to keep track of how did we reach 6 here, right? So I start with 3. After that, I can go in both directions, 5 and 1, right? So I go in both directions, 5 and 1. Uh, when I'm at 5 directions, I go to 6 and 2. I found 6, so I exit that particular loop saying that I found 6. And then I store the answer how I got to 6 into a list. Okay. Same goes for 7. Okay. I have parent, parent, parent. So if I reach 6, if I found 6, then I can go to 6 parent. I can go to 5 parent. That is going to give me the list here like this. So from 6, I can go to 5. I can go to 3 because I have the parent pointer here available. Okay. So I can do a DFS search here, or I can also do a BFS search. It doesn't matter. So I can just do searches on this particular tree so that I can get to the node. As soon as I get to the node, I have that node, and from there I can track, I can trace back the parent. Okay. From there, I can trace back the parent all the way to the root node. Okay. Let's do that. Okay. So that is going to make our time complexity of O of n plus O of n, because we are first searching P and then we are searching Q, right? And by doing that, we have the range of node 10 raised to power 9. Every node is having unique values in it. P is not equal to Q, and P and Q will always exist in the tree. So these are the things that are known to us. And the range or the total number of nodes are going to be 2 to 10 raised to power 5. You're going to have at least 2 nodes and maximum nodes that you are going to have at 10 raised to power 5. Okay. So we can do that. So we need extra space here for storing this list. So that's why that list is going to take space complexity of, again, O of n for both P and Q. All right. So yeah, I mean, we can solve that. Let's try to solve it with that approach. Then we can go and check if there are any other approaches. Okay. So uh, path, just call it get. Define a function called as get path. Okay. So for any given node n, it is going to return the path. Okay? Return the path. So first of all, we have to get the node first for that. Okay. So we have to search the node n. So let's say f. Okay, p is already given to us, it says, right? Oh, we don't have to parse everything. The p is already given to us. If p is already given to us, then we can just do parent, parent, parent and reach to the, yeah. So, okay. So if p is already given to us, we can just do parent, parent, parent. Okay. So p dot parent, we already know this. Okay. While I can just say n dot parent. While this is not none, okay, all I can do is I can just create a path here. So I can just say path is equal to just here like this. There's another way of solving this, by the way. We'll take a look at that in a bit. So this is the path and dot parent, uh, path dot append. Okay, path dot append. I'm going to say n. Okay, and n is equal to n dot parent. So I got the path here. When I check the path for p, it's going to be get path. I need to send p here. Okay. Other thing I can do, I can just do get path for q. So it will give me the path for both of them. This path is basically going to have nodes in there, and then I can start parsing the path for p and q from the left side, from the right side. Okay. Uh, yeah. So we can start parsing the path for p and q from the right side. Okay. Let's do one thing. Let's check who is the longest. Okay. Let's check who is the longest. Let me just think. Can I just do it from who is the shortest? So shortest, I just start from here directly. Yeah. So what we can do is we know that we have to pass the whole thing here, right? So we can start by taking what is the maximum length, or what is the max index to start with. Okay, max index to start with is basically going to be here, which is minimum of the length of both. So I can say length of path p and length of path q. Okay, so whatever is the minimum, I'll start from there and go reverse. Okay, so for I in range max index, okay, I can start from here, uh, -1, because length -1, we have to do length -1 reverse direction. Okay, in this case, if path p I, okay, we have to return the node, or we have to return the, okay, we have to return the node here. If path I is equal to path qi, then we found our answer. Then we have to just return path or q, any one of that I. Okay, we just return that. This should be it, right? So we can take an example here, 6 and 7. So 6 and 7. So the path is going to do one thing. It's going to take 6 here. Then I take 6 and append it to the list here. So 6 got appended. Oh, okay. Sorry. I need to do a reverse here, because this appending is basically going to create it like this. So first 6 got appended. After that, 5 got appended. After that, 3 got appended. Okay. So because of that, the list is basically reverse. So first 7 got appended, then its parent got appended, then 5 got appended, then 3 got appended. This is what is happening. So if that is what is happening, then yeah, I mean, we can do reverse here directly. Path, let's just send -1 path here, or we can also start by looking from the right side. Okay, start from right side, whichever is going to have the most common one. Uh, First one that matches is going to be your answer. Only thing is you have to make sure that you align them properly like this. Okay, so you start. Yeah, I mean you can start from there, or you can just do this minus one thing, and that should also work. Okay, the in reverse direction. So I'll just reverse this list, and that should also work. Okay. Reverse list here, and it should get your path P, return the node. Okay, let's try to check this if it works. Output is null. I would output null for this. P is 1. So the paths are basically going to be 6 and 1, right? So path is first I append 5 there, and after that I append because I'm reversing it later. So this is what the path is going to be. P comma 5 is the path, and the um, path for 1 is basically P comma 1. If that's the case, then I start from max index, which is 1. This is 1. Then after that, this should match, right? So why is it not matching? Uh, Path P, path Q. Okay. What is the mistake here? While n dot parent, path dot append, n is equal to n dot parent. We took the path, we reversed the path, send it here. This is going to be path of P, this is going to be path of Q. I go from the maximum index, so maximum index is 0, 1 here. So start from 1, then it's not matching, and go to 0. 0 would match, and then it should return it. Why it is returning none? Why is it not returning anything? Okay, why would it do that? What about this? This case is 5 and 4. Okay, so 5 and 4 worked, but this 3 also didn't work. Returning null. It's not matching this. The reason of that is, do I need to match the values? Uh, let's just match the val, because we know that the values are. Uh, no, it won't work like that because it's not going to match the values. It's going to match the let me. Okay, would that not match? Sequencing is different, I guess. Here, start from -1, right? So let's do one thing. Start from because we want to go in the reverse direction, right? So because we want to go in the reverse direction, let's go in the reverse direction. I think that would be better. But even when we go in the reverse direction, we have to make sure that we align them properly so that we increase both of them together at the same time. Um, this is taking about 20 minutes now. 3, 1. Let's just print this and 6 I path path. What is it returning? Returning path. Uh, okay, it says there's only one node here. Oh, yeah. This should be n, not. There you go. It works now. So we have to get the whole path properly. The whole path was not getting correct, selected properly first. So yeah. Earlier, what was happening is I was going to this particular point. I was just stopping here. I was checking if its parent is none. If its parent is none, I'm exiting that loop. So this three was never getting added. That's fine. Hopefully this works. Yeah, so that works. Okay. Now let's think about a different approach here. All right. So let's take a look at this particular problem. So what is given to us? You are given P and you are given Q here. Okay. Uh, there's one more technique of solving this. It is called as I think parent matching or something like that. And then you have to swap the values. So what is the idea behind that? Is you start with P and you start with Q. Any value of P and Q. Okay. So you are given 5 here. You are given 5 here and your Q is 1 here. Okay. Now, what will you do is you will go to its parent. At the same time, you'll go parent of Q. If they both match, you return the answer, which is basically the common ancestor. Okay. Now, if your value of P is 5 and the value of Q is 0, okay, the value of P is 5, value of Q is 0, you take parent of 5. You also do parent of Q. It is not going to match here. Okay. After that, you again change P to parent of Q. Okay. Then you, sorry. Yeah. After that, you change P. Now your P is pointing here, your Q is pointing here, right? So after that, when you try to move P even on top of this, it is not going to move there. Okay. Whereas this can move here. All right. So Q will move here. Now P is pointing to a none. As soon as P is pointing to a none, what we can do is we can move that P and point it to the original Q here. Okay. Move that P and point it to the original Q. All right. Now P is here and your Q is here. All right. So go to the parent and go to its parent. And now Q became uh, none. Okay. Because Q became none, you move the Q to the original P here. Okay. And now P parent and then Q parent are both going to point to the same answer, which is going to be your lowest common ancestor. Okay. So you start from, if they are in the if they are at the different level, then eventually they will map, because whenever one becomes none, you point it back to something, you point it back to the different value of it. Okay. So if it's a P, you point it to the older value of Q, or you point it to different value of Q, and so on. Okay. So I think that idea is what solved it in the first time. So you start with 5, start with 4. So let's say you start with 5 and 4. Okay. Your P is here and your Q is here. So you take P and go P and take P and move it to 3. So you're pointing P to the parent of P, which is 3. Now your P is here, right? Let me take, let's take this particular. This is what we have. Let's say you are your Q is here. Sorry. Let's say your Q is here and your P is here. Okay. What you do is go to the parent of P. Now your P is pointing here. At the same time, you go to the parent of Q. Your Q is pointing here now. Okay. After that, you go to the parent of P, and you also go to the parent of Q. So now your Q is pointing here and your P is becoming none. As soon as P becomes none, change the value of p to this particular q. Now your p is pointing here, let's say. Okay, you move it here. Your p is pointing here, and then your q is pointing here. So after that, you move this q to the parent here like this. So as soon as you move the q to parent, you move the p also to the parent. Now your p is pointing here, and your q is pointing here. Okay, p is pointing here, and q is pointing here. Now move this to the parent here like this, and move this also to the parent. Your q became none. That means you have to change the value of q back to p. Okay, so that means once you change the value of q back to p, you are basically going to have same values here. As soon as you have the same values, you have reached the least common ancestor. That's the idea of what we're trying to do here. So we just keep on looping this p and q until one of them becomes equal, or they become equal to each other. Okay. Let's try to code that. So what you want to do is while um, while p give me a second, while p or q. Okay. So what we want to do is we start. Okay, let's do this. So let's start this. We want to do p is equal to p dot parent. Okay, and q is equal to q dot parent. When do you want to do this? If p not equal to, if p is equal to q, then you just return either p or q. That is going to be your answer. Okay, if not, then you want to do this. You have to move parents like this. Okay. uh okay, at any point, if one of them becomes none, you want to uh, swap the values. Okay, so if p if p becomes none, okay, then swap the values. Okay, p comma q is equal to q comma p. Okay, or if q becomes none, you want to swap the values. Okay, so this is how you swap the values in Python, right? So p becomes q and q becomes p. How long you want to do this? You want to do this as long as you want. Okay, so you want to just do this as long as this does not become true, and when that becomes true, you just return this. Okay, let me just think. So we start from 5 and 3. These are not equal, so p will go to the parent, q will also go to the parent. Okay, you check that p and q are equal, you just return p. Okay, after that you have second condition where p is here and your q is here. So you take p, move it to the parent. Okay, take q, move it to the parent. Take p, move it to the parent. Take q, move it to the parent. Now p became none. If p became none, uh, then you want to swap the values. Okay, we want to swap the values back to here. P became none. We want to move it back here. The original values. Okay, you want to move it to the original values. You have to store the original values somewhere here so that it can go back to the original values because we're changing the pointers here. Right. So let's save them in the original values. Okay, original p is equal to p. Okay, original q is equal to q. We are pointing them to the original values here right now. Okay, if p becomes none, then point p to original q. Okay, if q becomes none, then point q to original p. Okay, but next time you want to point it back to its own. Right. So we want to swap the values here. Okay, so we should be swapping, not q. Then if any one of them becomes null, then we should be swapping. Uh, okay, this should work actually. Let's try. Right, so we can just swap it back to the original values. Okay, so it should work. So if at any point if p becomes null, bring it back to the q. At any point when q becomes null, bring it back to the p, so that you can finally reach to the common ancestor there, and you are guaranteed to have a common ancestor. So that should work. All right, let's move on to the next question. We spent quite some time here. This is a premium question. I need to send you. Let me send you a screenshot of this. You should be able to have that question now. You can zoom in and read the question if you want. All right, so the question says, you're given a nested list with a weighted sum. Sorry, you have to calculate the nested list weight sum. All right, let me just check it. So you are given a nested list for each element is either an integer or the list whose element may also be an integer of other list. Okay, so you want to get okay 4 ones at depth 2. Okay, 1 2 at depth 1. So 1 into 2, 1 plus 1 into 2, 2 into 2. Okay, depth. So what is given to you? So this is a list which is at the depth 2. This is a list which is at the depth 1. This is a list which is at depth 2 again. So what is the depth? Multiply each number with the depth. So 2 into 1, 2 into 1. That becomes 4. Plus 2, 6. Plus 4, 10. That is how you get a 10 here. Okay. If you check this example, 1 is on the depth 1. 4 is at the depth 2. So 2 is going to get multiplied here. 6 is at the depth 3. So 3 multiplied by 6. So 6 3s are 18 plus 4 2s are 8, 26 plus 1, 27. So that is what you have to calculate. So you have to calculate nested list weight. All right. And then you are given, this is an interactive function where the nested integer class is going to have functions, which is if it is an integer, if it's think it's if it's not an integer, then it's going to be a list. Okay. You can get the list by doing get list. You can get the integer by doing get integer. What else is there? You don't need others. This is just telling you that this is that interface. Okay. Return the sum of each integer multiplied by its depth. All right. So what you have to do here is you have to know the depth of each of the trees first, each of the each of the nested list, so that you can multiply them. Okay. So what we can do is, so One thing we know is that it's going to be a list here. So this nested list is a list first of all. Okay. So if it's a list, I think we can do a loop on that. Let me just make sure of that. This is a list of nested list. Okay. So this is a list of nested integers. Sorry. Okay. So this already is a list of nested integers. So you can do a for loop on this. Okay. Nested integer is this particular class. So we can do a for loop on this. And when we start out, the depth of our for loop is 1. Okay. If the first element that we encounter, if it's an integer, then you multiply with the depth of that. Okay. If it is not, then you have to do a get list and increase the depth by 1 and then recursively call it. Okay. You have to do recursively this. So I'm going to do recursive here. Start out with 1 depth. After that, as soon as you get this, you have to solve this first. So in order to solve this, you have to recursively call it. Okay. So recursively calls to solve this. In that recursive function, you need two things. You need the list and you need the depth at which it is right now. Okay. So let's first, uh, if you check what is the time complexity of this, you're going to visit each and every node at least once. So the time complexity is going to be total number of nodes or total number of values that you have here. Okay. Its length is 100 and not more than that. Depth is 50 and not more than that. So recursive functions can be used because 50 depth is fine. I'm not sure how much is the maximum depth. I'll have to look it up. But yeah, 50 depth is fine. So first thing that we have to do is we know that this is a list. Okay, so let's call this nested integer. Okay, in your nested list. Okay, and we need the depth here. So depth is 0. Here we can check if ni is integer, right? So that's the function that is given onto us. So if it's an integer, then you will need an answer here. Your answer is basically 1 to start. Sorry, your answer is basically 0 to start out with. So this depth 1, 0. Okay. So answer plus whatever the value of ni is, multiply with the depth. Okay. Whatever the value of ni is, multiply with the depth. So I think returns the single integer that this integer holds. If it holds a single integer, returns none. If this, okay. What is this? Returns the nested list. That just if it holds a nested list. Returns none if this measure holds a single integer. Okay. Holds a single integer, returns none if it holds a list. If this holds a list, then it's going to single integer. Value. Okay, let's just try this first. Okay, let's try this and let's try to print the answer first. I need to check if this is working, if the integer is getting multiplied correctly or not. Okay, if it is this, then multiply with the depth. Let's try this. Okay, so it's a nested integer, right? So I think I need to do dot get integer here. So it should work. Maybe is it what you want? Okay, yeah, there you go. We are printing 2 here. We're printing 2 because 2 multiplied by 1. Okay, so this works. So this is what we have to do. We have to get the nested integer and get the integer from there. Okay, and that is what is also given here. So it returns an integer here. See this? So return type is integer. Return type of this is an nested loop. All right. If it is not an integer, else. Okay. If it is not an integer, then I have to call a recursive. Then I have to do a recursive call. Okay, I have to do a recursive call on what? I have to do a recursive call on ni dot get list. I have to do a recursive colon generate get list, which is going to give me the list, and my depth is going to be +1. Whatever my depth is right now, I need to do +1 on that. Okay. And my answer is basically summation of solution of this. So whatever this is going to solve, that is going to be my answer. Okay. All right. This looks good. So let's just define a recursive function. The recursive function is this, where we need your nested list. Okay, nested list, and you need the depth. Okay, depth will come out from answer outside. You also have the answer, which can stay outside here like this. And return recursively nested list. Depth is 1. Correct. Let me run this. Answer is not accessible outside. Fair enough. How do I make sure that I have access to the answer outside? So I have depth here. I think I have to send answers here. That's all the problem. Let's just try. So whatever the answer is here, start out with 0. Sorry, I need to return answer here. Completely forgot about what is it going to do. Okay, so this didn't work. This worked only in one case, which is this. This is my answer. I'm returning the answer, which is, let's do one thing. Can we make this answer somehow global, accessible inside everywhere? This is for 0. Oh no, I need to get the temporary answer here, right? My current answer is 0. My current answer plus. Current answer plus. Okay. And to return the current answer here like this. Which is going to be the summation of this. There we go. So I need the current answer here because in the loop I need to multiply it. I don't need an external value there. So this is a recursive function. This recursive function is going to go through all the list, and it's going to solve it for us and give it the answer. Let's try to submit this. This works. Yeah, I mean, the reason we thought this is a recursive function is mainly because we can see that we are trying to solve it one level at a time, and when we go into another level, we'll have to recursively call that same function again and again. Okay. So, and outside we know that it's a list already because it's given here. So this is a list. Okay, this is a list of nested integers, and I can just check if it's an integer. I can directly do a multiplication. If it's not an integer, then I need to do the summation and return the answer here like this. And your recursive function should return something, right? So call with the same one. Yeah, same thing. You have the total with the depth plus 1 and all. Same code. BFS, this is interesting. What it says is you can also do a BFS. BFS can be the depth 1, total is 0. You start with Q, which is your nested list. Okay, and then you check the length of the queue, pop answer, extend to the left. All right, let's carry on. Sure. Let's move to the next question. This is again a premium question. So I'll share. Let me share this question. Sorting किया ना हमने ठीक. Uh, that's the image for dot product of two sparse matrix. All right. So the question says you are given two sparse matrix. One is number one and number two. Sparse matrix is the matrix which has a lot of zeros in it. So is it a lot of zeros or something else? Initializes the vectors dot product. Okay. So this is 10023 and this is 023. You have to multiply this 1 with this 0, 0 with this 3, 0 with this 0, then take the summation of whole thing. All right. A sparse matrix is a vector that has mostly zero values. You should store the sparse matrix efficiently and compute dot product into sparse matrix. Okay. So what it says is you're given two types of vectors. I keep calling matrices. These are vectors actually. The vector is having this list of values. This is another list of values. And this vector is interesting because it has a lot of missing values, a lot of zeros in it. Okay. So this one has two zeros. This one again has two zeros in it. All right. You have to store it in such a way that you're not using a lot of memory. So you have to store it efficiently and compute the uh, multiplication. Okay. So you do this one multiplied with the this value here. So we are index multiplying this. So one is getting multiplied with zero, then this zero is getting multiplied with this three, and so on. And then you take the sum of everything. So most of them are zero. So what we can do is, in order to efficiently store, we know that most of these are zeros. Any non-zeros values, you should store them. Okay, any non-zero values, you should store them. Anything which is zero, don't have to store them. The way we store them is by using a dictionary. So at zeroth index, I have one. At third index, I have two. At this index, I have three. So I just need a dictionary, which is value index, index and non-zero values. Okay. So I just need a dictionary which is like this. I need to go through all the numbers. So n in nums, enumerate. So let's just enumerate this. I'll get index and I'll also get the num. If I is not equal to zero, sorry, if n is not equal to zero. If n is not equal to zero, I can just store the index and whatever the value is. Okay, so that is how I store the values. Dot product. Okay, so when I want to do the dot product, I can use this particular thing and I can check if the indexes are present and just multiply them. Okay, so I can get any one of the so if I take these two examples, then my non-zero indexes are going to be this. So for the number one, it is going to be zeroth position. I have one. At third position I have 2, and at fourth position I have 3. Okay, and for number 2 I'm going to have at one position I have 3, at third position I have 4. Correct. So you have one position पे 3 present है, and at the third position I have 4. So key is the index, value is the value for at that particular index. Okay, dot product. So what we can do is we can just take if 0 is present here, I can check if 0 is present here. If it is not present here, that means that 0th index is 0. Okay. So multiplication with 0 is going to be 0. So no need to do anything there. So we can just iterate through the vector dot self here, so that it is assigned to the class. VC index in this. Okay, let's just go through this. We can also get the value. If we do items here like this, we can get the values. So we can just get vector index and vector value. Okay, and since we have that, we just need to check if the vector index is in. Okay, if vector index is also present in self dot this guy. Okay, self dot text. If it is present, then my answer is basically start with 0. Okay, so my answer answer is vector value multiplied by. Okay, so this whatever the vector value is, multiply that with the vector value for the same index in the other list. Okay, and then you return answer. Okay, so what we are doing is we are trying to multiply these two together, this dictionary and this dictionary, based on the keys. So if the key is matching, we get the multiplication, save it there. So we are going to iterate. Let's say we are going to iterate over this particular dictionary. 0 is not present here, so nothing is going to happen here. After that, we check 3. Is 3 present here? Yes, 3 is present here at position 4, and its value is 4. Okay, so you get the value of 3, multiply it with the value of 3, which is here. 4 to the 8. 8 should be your answer. Now you go to 4. 4 is not present here in the keys, so that's all your answer is. What happened? Ah, this is the fraction. Not all right. So that's how you solve it. Fairly straightforward question. Nothing too complex here. Now the question also says there's a follow-up here. What if one of the vector is sparse? If one of the vectors is sparse, then again you have to do the same thing, whichever vector is sparse. So let's say this is a sparse vector. That is a sparse vector. You can still use the same dictionary to multiply with the non-sparse vector. Because everything else is going to be 0, you can directly jump the keys. So 0 is going to get multiplied with the 0th index here. If it is not sparse, you'll get the value. 3 is going to get, we are directly jump to the third index. Multiply that with this. Okay. Then you go to the fourth index. Directly jump to the fourth index. If it is available, then get the value 3. Obviously, it is going to be available because they are of same length. The length of both of them has to be same. That's how vector multiplications work. Dot products work. If it is a sparse matrix, even in that case, you can solve this by using the same technique. Only thing is, you will not create this dictionary for the non-sparse thing. The non-sparse thing, you'll just keep it as it is. Okay, let's move on to the next question. Merge a sorted list. It's an easy question, so hopefully we'll solve it quickly. We are given two integers, integer arrays num1 and num2 sorted in non-decreasing order. So this is present, this is second. Both of them are sorted non-decreasing order. You are given value of m is equal to 3, value of n is equal to 3. What are these values? merge num1 and num2 into a single array sorted in non-decreasing order. Okay. The final sorted array should not be returned by the function, but instead be stored in the same array of num1. To accommodate this, num1 has extra spaces. All right. So what they're saying is you have this num1 and you have this num2. You have to take this num2 and insert it, join with this particular num1. Okay, in such a way that num1 is getting changed. All right. So what can we do here? So num1 and num2 has to be merged. Num1 already has extra spaces in there, so that num2 can be accommodated here. What can we do? Uh, so we can start with, so we have to insert the value here, right? Okay, so we have to insert the values here. Let's start with this last value 3, and let's start this last value 6. Okay, whichever is higher takes this spot. Okay, after that I keep this pointer still here and I move this one pointer. I take 5 and I compare it with 3. If it is bigger, then I insert 5 here. Okay, then I go to 2 and my other pointer is still pointing to 3. So I compare these two. I can see that this value is larger than 2. It is larger, and this spot is going to be taken by this value here. Okay, then I move my this pointer to this value. All right, then I check this value with this value, this 2 with 2, same. I can move it here now to the next empty spot. All right, so the idea is, let's take this example here. So you are given, so let's take this example here. So we are given one, we are given two lists here like this, right? We are given two lists here. Don't need this M3, not required. We don't need this 3 also, so we can get rid of this. Okay. So what we can do is we can start with by filling from left to right to left. Okay, we can start from here. We can start from one pointer here. Okay, so one pointer is pointing here. Let's call that n1 pointer because it's for num1. Let's call this n2 pointer. Okay, we can check both of these numbers. Okay, if n1 is if n1 is less than n2, value of n1 is less than n2. Let's put the base case first. Okay? If the value of n2, same, if the value of n1, the value of n, sorry, the value of n1 is less than value of n2. Okay, that means you can use this value and put it here. Okay, so do that. So take the 6 and put it here. All right, and then move this n2 to this point. Because this is already placed, you can move this n1. No, sorry. I'm not checking here. When we started out, we said check something else and check. So what we are saying is your n1 is here, not there. So your n1 is here and your n2 is here. Okay, now it is right. Okay, and then you check. You want to start filling from here, right? So you have a fill pointer, which is going to point to a point from where you want to fill. So let's call it F because it is going to fill. So if your n1 is less than n2, Okay, if your n1 is less than n2, then move this to the fill pointer. We fill this value, move the fill pointer here. So your f is pointing now to this particular position. Okay, so your f is pointing there, and your n2 is placed here. So this became 6. Okay, so this became 6 now. What about n2? It will move to this particular point. Okay, n1 is still pointing here. So again check. n1 is less than n2. True. Then use this value and fill it here now. So put 5 there. You put 5 there, and your n2 will move ahead because you have changed n2. Okay. And your fill pointer will also move here. Okay. Now you check n1 and your n2. So n1, this condition is failed. If this condition fails, then what we want to do is we want to take this value and put it here. So put 3 here now. All right. And move your pointer of n1 here. Okay. 3 there and move the pointer of n1 there. Your n2 is still pointing here. Compare these two. Uh, I'll just call it less than or equal to so that we can move this. So take this 2, put it in the fill place because fill place is here now. Okay. That will basically fill your whole list automatically. Let's try to code this quickly. How to merge this, right? So what we are saying is we need 3 pointers n1, f, and we need n2. Okay, so we can use that. So f is basically your m plus n minus 1. That is total number of in m plus 1 minus 1. Okay, and your n1 is m minus 1 because that is the total number of values you have, and your n2 is n minus 1. Okay, so that, and then how long do we fill this? We fill this. Just think how long do we have to fill this? Okay, let's fill this all the way to the when until and unless we pass the whole list, until and unless we pass this whole thing f. Okay, so underscore for range f. Okay, we want to pass the whole thing until and unless we reach the whole f. You can do that, or you can just put f here directly. That should also work. Okay, if I put f here, then I start with m plus n minus 1, go all the way to 0. Should also be fine because we are anyways moving f always. Okay, condition 1, if your nums n1, okay, is less than or equal to nums n2. This is true, then your num1, nums1, this is nums2, correct? Your nums1 f is basically your uh, larger value, which is from here. Okay, and then you do n2 minus 1. Okay, else opposite of this. Okay, else n1 f is equal to n2 f is equal, sorry, n1 f is equal to n1 and 1. Okay, so same pointers of n1, and n1 will move by 1 distance. Okay, all right, this is, we can put this. All right, let me just think if they're in corner cases here. The corner case here could be if you have n is 0, then n2 becomes minus 1, and this will go out of index. That goes out of index. Then we have to think about that values too. Okay. So do this, okay, do this particular thing if n1 greater than 0, sorry, greater than or equal to 0, and n2 also greater than or equal to 0. This only do this when this is true. Okay. Else, if that is not true, if n1 is greater than or equal to 0, that means you just have to do this. Okay. Else, you just have to basically your n2 is greater than or equal to 0. In that case, you just have to keep on replacing the values of n2 into the fill. Okay. So we'll do this if this condition is true. Else, if we have passed everything in the n1, but we still have values in n2, then we'll have to use those values to put it back into n1. So hopefully work. Just think. You have nums1 and nums2. Let's take this example. So your n1 becomes n1 is pointing here. Your n2 is pointing here. Okay. Your f is pointing here. Then if it is greater than 0, which is it is also greater than 0, then you take the value of n2, check against this value. Whichever is the bigger value, you put it into the fill. You move that. So n2 is greater, so you moved n2 here. All right. After that, you kept this as it is. You moved n2 here. You kept that as it is. Check this value. You again moved, and then you are already done now. So you don't have n2 any longer. So if n2 is not present, then whatever is present in n1, we'll have to replace it there. Yeah, so we should go. Nums1. Nums. Okay, there you go. Works. All right. So we basically take the values which would go in the end and start replacing, because that is where the gaps are. Okay. Start replacing from right to left, then you will end up overwriting the values here. Start filling the gaps, and then you will get the answer to it. Okay. Let's check the tutorial if there is any 3 pointers. This is what we did. Okay. We can merge these conditions. That's what they're doing. Start from end. Yeah, I think this is what we did. We started from end. We start this P is basically your F. This P1 is your N1. This P2 is your N2. Then we started to fill it. So, yeah, same loop. So one thing they did is they did not do this. They only did this. Okay, because P2 only needs to be placed into the num list. If P1 has reached already, then that means P1 is already in the place. So, all right, let's move on to the next question quickly. Copy link list with the random pointer. So, send the question. All right, go ahead. You can start reading the question. The question says that we are given a linked list which has random pointers, and we want to copy list with random pointers properly. Okay, so you are given this list 7, 13, 11, 10, 1. Okay, and then there is null. All right. you want to create a copy of this list. Okay, you want to create a copy of this list such a way that none of the pointers from the new one will be pointing to an old one. Okay, make a copy of this, right? Deep copy. The deep copy should consist exactly n brand new nodes where each node has its value set to the value of its corresponding node and random one. None of the pointers should point to the nodes in the original list. Okay. The linked list is represented in the input as n for each node to represent value and random index where val. Okay, that's true. Creating a copy is directly easy. The problematic part is where we have the random pointers. Okay, if I want to create a copy, all I can do is just take this value, create a copy of that, and then whatever, take the next value, create a copy of that, and join those two together. Take the next value, create a copy of that, join it. Take a value, create a copy, and join it. Take a value, create a copy, join it. Okay, that is straightforward. The problem is with this random values. Okay, right. All right. So what we can do is, so we have this randoms here, right? So this is random values here. So when we create a copy, we need a way to create the randoms properly. So when I create a copy, I can have the old one and the new one. Okay, let's do this. You have this. This is the original. Okay. So if this is the original, what we can do is we can now create a. We need a lookup actually, so that we can join them properly. Okay. So this lookup is going to have old. What is the new node? Okay. So first we go on creating this particular thing. So first value is this. Okay, so the old node is whatever the node is here. So this is the old node 7. Okay, and it is pointing to the new node 7 dash. Then old node is 13. Okay, it is pointing to the new node which is 13 dash. Okay, we create a dictionary which basically is having old and new nodes. All right, why do we need this? Is because uh, when we want to create the randoms, okay, we will go through the old new list. Let's think. When we want to create the random, so this dot random is going to point me to some value here. Mm, uh, okay, so 7 dot random is pointing to null here. So 7 dash dot random will also point to null. Okay, that's fine. 13 dot random points to 7. Okay, so 13 dash dot random should point to the 7 dash. And how do I know it should point to the 7 dash? Because I go to 13 dash, sorry, I go to 13, old 13, and I check who is its random. It comes out as random values this. Okay, and then I assign the value to the value of this dictionary which you have in the lookup. Okay, that should work, right? So what we are doing is we have 7, 13, and all of these values. This is old, this is new, and All we have to do is just take the random values and assign them properly on the new list. Uh, Next is fine. The random is what might create problems. So for that we need this lookup. Okay, let's try to do that. Uh, Still, right? So let's call this lookup. This is a lookup which is an empty one. Uh, let's call this duplicate. Okay. Uh, Head. Okay. So let's take the head and create a duplicate of that. Second. Let's just check. This is going to be a node. Okay. So we need a node here, and duplicate. Uh, that is here. We want to iterate through the whole. We want to iterate through this and keep on creating the nodes. Correct. So while uh, and let me just keep the old node, old head. Okay. Old head is my head here. While okay, let me just only the old node. So my old node is my head node, which is my head node. So I just take this value. If this is not null, then my old node is equal to old node dot next, so that I can keep on moving next. Okay, before creating the next, I need to create a copy of this old node. Okay, if I know that this is not null, that means old node, new node. New node is basically node which has x value in there, first one, which is the value. Okay, so it's going to be your old node dot val. You create the old node. Okay, and then this we need a map here. Just create a map right now. Just look up. Your dictionary is your old node, and your value is basically your new node. Okay, which is this one. Okay, all right. So you have this new node which is present into your lookup now. Let's just do it this way. So we do need this old node here. So this old node is basically just keep on moving until you get the whole until you create the copies. So this has been copied now. All the nodes have been copied. We don't have connections yet. We don't have next connections yet. Okay. Now what we can do is we can again iterate through this old node now. Okay. Your old node is basically your head again, which is your old head that you have stored back, and you are going to iterate now. Okay. When you iterate this time, this looks fine. Old dot next is fine. You want to take the head that you have here, right? Okay. Look up whatever is the new node. Okay, so this is going to give me the new node now. The key is the old node and the value is the new node. So this is going to give me a new node. New node dot next is equal to, I need to use the lookup here now. Lookup and old node dot next. Okay, so I'm using this lookup table to start creating the connections here. So what I did is now I'm starting to again go through this particular list here, go over this particular old list. 7 new dot next is equal to 13 new. Okay, 7 new is equal to 13 new. 7 dot next or 7 new dot next is equal to 13 new. Okay, I want to do that. So for that, I need to do this. So I need to get the lookup value dot next, take the lookup value, old dot next, and this is what it should look like. This thing. Uh, uh, just thinking, what about nuns? Okay, if it is none, let none point to none. Okay, so that we can handle nulls gracefully here. Okay. This will point properly. What about the randoms now? Can do the same thing for random dot random is equal to basically old node dot random. From the lookup, I'll get it and return lookup old node head. This is what we need. We don't need this lookup. Okay. So this lookup old node's head is going to give me the back. Works right. We have a lookup which has none values too in there. If we get the old node, which is going to be present dot next. Okay, old node is null. I think it should work. Yeah, should work. All we did, we just rerouted all the pointers properly using the lookup file that we have here. Submit this. Okay, works. Let's check the editorial one. Happen because we and it will proceed in iterative is what they're iterating through. Does not model it as a graph, instead treat it as a linked list. Traverse the linked list, start at the head of the linked list. So given linked list, this is your prone linked list. So given linked list is this. If the random pointers points to the random pointer to my table. So start with here. This is pointing here. Take the random pointer and create another pointer which is C dash. All right. Next pointer and then get the next pointer too when you encounter it. All right. Then we repeat step two until we reach the end of the thing. This also looks easy enough. All they did was they kept track of was it visited or not. If it is visited, then they'll just return you the visited node. Okay. Which is similar to what we did here to the lookup. This approach is iterative with no extra space. Okay. Uh, you can tweak the original list and keep every clone next to its original node. This interleaving of old and allows us to solve the problem without extra space. Okay, what they're doing is okay. The next, just move it here. Okay, all right, and then Okay, so this is interesting one. So what they are saying is, if this is a given list, okay, A, B, and C, if this is a given list, the blue ones are the next pointers. The red one are the random pointers. Okay, you start with A, and because that you're at A, create a clone of A and insert it between A and B. So this got inserted here. All right. So this got inserted here. Then you are at B, create a clone of B and insert it between B and C here. Then you are at C, create a clone of C and insert it here. And there's no need to insert anything on the top. Okay. After doing that, you can again start going through the whole list and then assign the random pointers. So we know that this A, the random pointer is pointing to C. Okay. That means the random pointer for A dash will be pointing to the random pointer of this next. Okay. So random pointer of A dash will be pointing to random pointer of C dash. Sorry, random pointer of A pointer will be pointing to C dash, which is nothing but next of your random pointer from the original one. So next time you just use the random pointers and join them. Yeah. All right. So only problem with the third one is you will be changing this head, okay, which might not be intended in this particular case. Because you are interweaving some nodes here, you end up updating that head node to something else, okay, which might be sometimes not expected. Again, whenever you see a linked list, you should learn about how to join the linked list. जो हमने last time पढ़ा था, merge कैसे करते हैं दो linked list by using that extra pointer. Second is inserting between two nodes, deleting from a linked list. You might have to learn all of this, okay, so make sure you brush up those concepts. Let's check. I can do one more question. Okay. K closest points to origin. Right? So you are given points here, and value of K is 1. You want to find what are the K position, K closest pointers to 1. Okay. All right. So anytime you see Kth, K, uh, I think I've told you earlier too. The easiest way of solving this question is by using a heap. Okay? Min heap या max heap करके आप solve कर सकते हो K, Kth वगैरह. Second solution is by doing a quick sort. Okay, quick select, not quick sort. Quick select. Quick select can also help us solve this. Because of a time constraint, let's just use a min heap here. Okay, so I think what we want to do is closest. So we want to do a max heap. Max heap is a heap which is going to have maximum here on the top, okay? And everything else, all the other elements are going to be smaller. Okay, the input that we have, let's take an input which is this one, because this has 2 points there. Okay. We need to get top two. So what we can do is first check the distance of this from 0. Okay. If your heap is empty, insert that. So you want to insert this index. Okay, whatever the index is, and what is the distance here? So distance is square root of 3, right? So square root of 3 is what the distance is. Comma, what is the index of this particular value, so that we can get it back later. All right. After that, we check what is this. Okay, this is square root of not 3. So this one is 0, right? 0 minus 3. 3 square, 3 square, 9 plus 9, 18 है ये. And this one is other one is when we go to this particular value, we check the square root of this. So square root of that is 5 as a 25 plus 1, 26. Okay, index is 1. Okay, now we can insert this value also. This value gets inserted because this is a max heap. The maximum value should get on the top. So max heap में maximum value यहाँ पर रहेगी. बाकी सब values, all other values are going to be pushed here. So let's push this value to. So let's put that value to s cube rt square root of 2 to the 4, 4 plus 16, which is 20. And this is at the position 2. All right. Now this max heap is greater than the k. If it is greater than k, then we want to pop the top element. So k, this one got popped. So what is remaining? That is your answer. Okay. What is remaining? That is your answer. 0 and 2. 0 and not 2. Yeah. So this one and this one are the closest ones. You can check that here. So minus 3, 3 and minus 2, 4 are the closest ones. So we need a max heap here. Let's create a max heap. Let's keep it an empty. That's for P, which is the point in points. Okay. Max heap dot heap q dot heap push. Okay, we want to push into the heap, into the max heap. What values do you want to push? You want to put square of p, right? So we already know that. What are the values of p? So p 0 square plus p 1 square. That's the distance from 0. We want to get the distance from 0, and we want to get the index. So we want to store these two things. First is the distance. First is the distance from 0, and second value is basically your index, which is of this particular value. So we need enumerate here. Enumerate here, that I can get the index also. All right, there you go. I get the values and enumerate it properly. Okay. If my length of max heap is greater than k, then I need to pop heap q dot heap pop. What do I want to pop from this particular max heap? Okay. And my answer is basically going to be whatever is present in my max heap. So my answer is for two things are present in my max heap. For first one is the distance, and I want the index in my max heap. Okay. And this is basically index of the points. Index of the points is what we need here. This is a max heap. By default, Python has min heap. So I want to put a minus sign here so that it gets converted to a max heap. So we should. Okay, so yeah, that's the heap के questions usually easy होते हैं. When you, this is little bit complex only because you have to find the distance. Now यहाँ पर square root, they are done square root here, but we don't really have to do the square root because even if you do the square and then do the square roots, you don't have to compare them. Square roots and squares are comparable. If the square root is smaller, that means squares are also going to be smaller. Solve this. Accepted. The time complexity of this again is because we are going to all the points. So it's going to be O of whatever number of points you have. Multiply that with log of k. Log of k, because you're doing heap push and heap pop. How many times? Whatever the value of k is, that many times from the heap. Pushing and popping from the heap is log of k. The next technique, the technique which is usually used, sometimes interviewer might say that don't use heap. They have sorted everything and then done returns. That's also fine, but this is going to increase the time complexity. Max heap and priority queue are same thing. Okay, max priority queue and max heap are basically same concepts. This is a priority queue because we are giving priority to this particular negative value. That's why it's called a priority. Binary search. Identify the key. In standard binary search, we would sort. Okay. What is binary search? So first we pre-compute all the Euclidean distances for each point. Okay, that's nice. So after that you can do a binary search to get the transfer. This is quick select, which might feel a little bit complex, but all it tries to do is just two steps, which is uh, partition and then merge. So it does partition based on something called as pivot, and after that you can merge those two partitions together. Quick select is also having the same complexity, which is log O of log n. One of the sessions I'll explain quick session. Quick select. All right, so we are done for today. Uh, Good questions again. If you guys get a chance later, make sure you revisit the recording. Recording are all uploaded, so you can go and revisit them. All right. Sure. If you have any questions, I'm here for a couple of minutes, or else let's meet tomorrow.